All right, so today I'm talking about upcoming Lustre features, a little bit of, a little bit of everything on the Lustre roadmap. And so you can see here, we're sort of planning, about 2 years in advance in terms of the major features. I mean, we do have, other features on our wish list, but it's always a challenge, resourcing and things like that. So, we do have ideas beyond this, but I try to keep it, pretty real in terms of what people are actually working on before they get into these kind of presentations. And so, as Peter mentioned, on the networking side, we have done a number of features in 2.15, and I don't know, by show of hands, I'm going to be covering some things that are, I could cover some things that are 2.15 related, or people would prefer more 2.16, who would prefer, covering a little bit about what's existing in the 2.15 release. Okay, so about half. All right, so anyways, 2.15, one of the interesting features for TCP is the cons per peer. And so what we found is having multiple TCP connections on a single socket for 100 gigabit and higher network speeds, you actually get, because TCP is relatively CPU intensive in terms of data copying and things like that, we actually got better performance by having multiple connections. And in 2.14, there was a tunable that you could use to set this manually, and in 2.15 it actually automatically has a heuristic on the network speed. So I think with 100 gigabit it's 100 gigabits 4 connections per TCP socket, and I think once we get to 400 it will be 5 connections automatically. And so this can double your performance. It's something that you shouldn't really have to do anything to tune, but it's a nice improvement for TCP. The other one that's maybe a little bit esoteric, the selection policy lets you do things like configure affinity for NUMA sockets related to your Ethernet interfaces or IB interfaces. This is important for big machines like DGX and things that has maybe 8 network ports and lots of CPU sockets and things like that. Moving forward, IPv6 is a feature that's been requested for quite a long time. The nice thing is we actually have somebody working on it. Neil Brown from SUSE is involved with this, and Oak Ridge. And so this will, again, be sort of more of an under the covers kind of feature, but it's definitely important as we go forward, especially with virtual hosting and things like that. For many sites, the storage network is not publicly visible, so you can just put it on a subnet, so it hasn't really been a high demand feature, but for cloud hosting this is becoming important. Better network health and network discovery, just making multiple network interfaces more seamless. And for also related to IPv6 is trying to remove having to specify NIDs directly in configurations. So allowing better either handling of host names or automatic discovery of interfaces. So you just have to specify one interface per server, and then it automatically discovers all of the other interfaces, and it can handle IPv4 and IPv6 NIDs. And so that's just makes it easier to host if your servers are moving around on different nodes, basically anywhere that they're started. It would advertise itself to the clients, and that just simplifies some of the management. On the client side, GPU Direct is a feature that is pretty important these days. It allows direct RDMA transfer of the data from the server through the IB interface or RoCE and directly into GPU memory. And so, I mean, the speed, it's not necessarily a huge improvement of performance because the transfer speed is the same, but it actually reduces the CPU utilization and, sort of feeds your GPUs a lot faster, right? And so that's interesting to many users these days. large direct I/O, and while that direct I/O is not necessarily a huge feature that lots of applications use, one of the interesting things that we're working with is to improve buffered I/O performance by essentially mapping automatically buffered I/O to direct I/O. And it turns out that the data copying isn't the high overhead, it's mapping pages in and out of the Linux page cache. And so by faking buffered I/O through a data copy on the kernel side, we can actually get much better performance. And as you see here, we took for the direct I/O performance, from 1 gigabyte a second up to 15 gigabytes a second. Pretty dramatic. I mean, that's with large I/Os, about 1 gigabyte sized I/Os. But we're looking at getting about 5 gigabytes a second, even with the memory copy for buffered I/O. So that's pretty significant. As was mentioned, client side file name encryption was added in 2.15. We did the data encryption in 2.14. And so we can do, even with the encrypted files, we can do file migration and mirroring with tools without having to do the key. So we can manage the space between OSTs. What still needs to be done is the encrypted file backup and restore. You could say it's so secure you can't back it up right now, but the truth is that it's essentially the kind of, there's a per file crypto key, and regular user space tools don't have a way to do that. And it's not a limitation that was imposed by Lustre. It has to do with the fscrypt API that we're using in the kernel. But essentially we're going to develop a modified tar that is able to back up and restore the keys properly. Further, the buffered I/O, as I mentioned, improvements to use the DIO, direct I/O in the background, other cleanups, and one other interesting feature, which I'll cover a little bit later, client-side data compression, is going to be, of course, done on the client, as the name implies. So what we found for, especially for flash usage, the cost per gigabyte is a challenge to get all flash file systems, and so some of the largest sites have all flash, but it still can be pricey. And so what we're doing here with the client-side data compression is to, we chunk up the file into small bits, 64K. It's variable, configurable if you need it, but we're going to start with that. And then it gets compressed, just before sending over the network. And then you pack these compressed chunks into a single RPC and send it to the storage, and then it's passed directly down to the storage. And like was mentioned, with the Kerberos, right, that's very expensive in terms of CPU usage. But one of the issues with Kerberos is that, it's encrypting the data on the client side and then decrypting it on the server side, and so it hurts the server performance, which is really your constrained resource. But with with the client-side encryption and with the client-side compression, this is only using client-side CPU resources, which you generally have a lot more of. And so we'll basically get, the full throughput of the server. And once you're constrained on the network or the storage bandwidth, you may actually see an improvement in performance by having data compression on the write path. Because, you have 4 or 5 or 6 clients doing the compression, you'll get an aggregate improvement in the bandwidth. And so there'll be a variety of compression algorithms. We're going to support the standard ones to start, and it'll be expandable in the future to add in more kinds of algorithms as we find good ones that work. Some other interesting things, of course, is that we'll try, as a starting point, in some cases we have to pass an incompressible chunk of data through all the way, because we can't actually expand the size of the data in the file. And so you'll be able to mark on a per chunk basis whether it's compressible or not. If it turns out that there's a large number of incompressible chunks, it may actually just be better to not compress the file at all. And so we'll detect that and stop trying to compress the file. And of course, the reverse on the read path. What else is interesting here? So other server-side improvements. We added some improvement. Fallocate, that's space allocation, is being improved for ZFS. LDiskFS optimizations, and I can't get into all the details of all these, but improving LDiskFS for the allocation. The other thing that's come up quite a bit, it's surprising. OSTs are often in the 500 terabyte range, and sites are wanting 1 petabyte OSTs these days, because for the erasure coding for the RAID level, it's more efficient to have a very large OST that has 40 disks in it, or 80 disks in it, because you get a faster rebuild speed, and the rebuild speed increases with the number of disks. But having a petabyte OST, that was larger than the whole file system for a supercomputer when I started, right? It was, I think I was looking back, the first Lustre file system was 300 terabytes, right? And that was 30,000 disks. And so, now we have one OST that's bigger than that. And people are already asking, can we get above a petabyte, right? And so, we do have to, have some limit, but it's getting into the billions of files. We have to have a more efficient internal management for that. And so these are some of the issues we're working on, better object management on large OSTs. The other one we introduced in 2015, parallel FSCK. And, we took the FSCK time, from multiple hours, again, on the large OSTs, down to the 40 or 50 minute range. And, leveraging all of the IOPS on, 40 disks. And it turns out, with Amdahl's law that, we did parallel FSCK for pass 1, which was, traversing all of the files in the file system. And now another pass has become the largest component of the time. And so we have to parallelize that stage as well, which is the directory traversal. But, so what used to be 7% of the total time is now 70%. And that needs some work as well. On the metadata side, one of the big improvements in Lustre 2.15 is the automatic space balancing. And this is really, the DNE feature has existed for many years. And it was intended originally, for administrator kind of control, so that user A would get on one MDT and we'd assign, a different MDT to somebody who has a problematic workload or something like that. But the truth is that today people just want it to work out of the box. And so, we've added in automatic MDT space balancing, so that in the top 3 levels of the file system, by default, it will automatically, every make dir that you do will automatically pick the least full MDT. If the space is balanced for the top level directories, it will just round robin across MDT. So you have a brand new file system, you're creating your top level directories. It's not going to say, they're all that equal, I'm just going to stick on one MDT. It will round robin across all of the MDTs, so that you get, a good distribution and usage of the metadata performance. And, we've had this in production at some sites already. And, they're getting, millions of creates and millions of stats per second just out of the box. And it's keeping, the space within a few % balanced. So it's very nice. Some other improvements, migration and by space with space balancing, or migration of a single directory. Those are, usability features. And some more in 2.16, we're doing some more optimization and robustness checks, so you can't specify an MDT as a target if it's, already full. Some people, aren't paying attention, and so you don't want to migrate onto an MDT that's already full. And what else? Just code and performance optimizations. Another interesting feature that's come up as workloads are going more towards genomics and financial and things like that, away from strict HPC workloads, is lots of more smaller files, right? And so we're seeing, workloads, like I was saying, with the DNE space balancing, that customer was creating, 15 million files per job, right? And that's pretty punishing. So what we've done is added in a feature. It's built on an existing feature called stat ahead. So if you know what read ahead is, which is byte level reading of the file data, the stat ahead is fetching attributes for ls minus l or r minus r ahead of the request from user space. And so stat ahead always only worked in directory order, and now we're starting to do stats in like predictive file name order. So if you have a workload that's creating, file 1, file 2, file 3, it will detect that the file name is incrementing and start predicting, it's going to fetch file 4, 5, and 6 attributes in advance. And it can do this in, sequential order, in strided order. So if you're fetching file, 1, 1001, 2001, etc., it will find those. And then the other interesting, important thing here is it's doing batching of those attributes. So instead of just fetching one at a time, which is what it was doing today, it's going to be fetching, 100 attributes at a time. And so that reduces the network overhead. The MDS can fill these requests more efficiently. And, with the predictive name detection, it can, get better performance. We saw, Peter was mentioning in the MD test for the IO500, we almost doubled the performance through this change, and it's totally transparent to the applications. And this is also, this batched RPC work is a preliminary for another feature which is coming up next, which is a metadata writeback cache. And so the writeback cache allows clients to create files and directory trees without talking to the metadata server each time. And so that reduces the round trip latency for doing, untar, like I said, genomics workloads. They're untarring some huge directory of, or they're building a directory tree of each, little segment of the gene. And so this allows you to create a directory, populate it, and do all of that without any round trip latency. And then when it comes time to flush that data out, you want to be able to aggregate the requests into one RPC so that it's much more efficient. And so the batched stat ahead is getting part of that feature landed in the 2.16 release, and then writeback caching will be coming in the 2.17 release. And so, like I said, it removes the RPC round trips. It's fully cache coherent between clients so that, one client will do, let's say, an untar, and if some other client comes in and tries to access that directory tree, it will flush out the parts of the directory tree that the other client is accessing it. It won't try to flush everything out of cache at once before the remote client can access it. So it's at least reducing the latency before other clients can access. And in our testing, this can improve metadata performance like tar and things like that by at least a factor of 10, sometimes 20. So that's pretty significant. And it can also integrate, there's in later parts of the patch series, it's integrating with the data cache, so you can do small file creates and then flush them out in batches. And so this code is well underway. We've already had the series in development for more than a year or a couple of years already. And it's just in this time right now, we're just getting the integration with quota and resource limits, memory pressure, kind of things, to make it suitable for production use. And then I think this is my last slide here. We're in the early stages of developing metadata redundancy. And so this is, to remove points of failure and harden the system. And so we're just looking at initial stages to do things like, mirroring some of the internal databases and move them off of the first MDT to allow the other ones to service some of these requests. And so this is, as it says here, this is going into, sort of far into the future, but, we're looking at what needs to be done at each stage so we can get something concrete, usable at each release. And I think that's it. So we're done.
Okay, thank you very much, Andreas.